Okay, now?
Yes,
Yes,
sir.
sir.
Okay. I think network is a little bit slow. So I don't know. So if there is any issue, please just unmute and just speak so that I should know, right? So there is a problem or not. Okay, fine. So let's start with some few more definitions. So one definition is argument. Now, what is an argument? So in a proof, suppose we have a proposition and we want to prove that proposition, then we shall give some arguments, right? Then what is an argument? Argument is just a sequence of propositions. So the definition is an argument is a sequence of propositions. Okay. Now the final proposition is called the conclusion. The final proposition of that sequence is called conclusion. Oops. And the other statements or other propositions, or you can say that all but the final proposition are called premises. Okay, this and this. Okay. Now note that whenever we will see a proof, then and we have an argument, then if you look at the each part of the sequence, that is sequence of that part of the arguments. So what is an argument? Argument is a sequence of propositions, right? But some propositions may not be an independent propositions, right? So if you start with two propositions, say P and Q, then the all the other propositions involve some combining propositions, right? So that is a compound proposition. So we will see when we see a proof, then we will see that. Okay. So therefore, we just generalize this statement, that is argument. So now we define that argument form. So this is the same thing. We are just replacing that sequence of propositions by compound proposition. So an argument form is a sequence of compound propositions involving propositional variables. Okay, and then we define when this argument or argument form is valid. Okay, so an argument or argument form is valid if the truth value of all of its premises implies that the conclusion is also true. So that's mean if you have an argument form, that's mean it is a sequence of compound propositions, right? And all the proposition except the final one are called premises. Okay, and the final proposition is called the conclusion. And when we say that this argument form is valid when if the premises, all the premises are true, implies that conclusion is also true. Okay, so we should not write a truth values. We can say that if the truth of all its premises, right? Otherwise, if I write truth values, someone may be confused with the truth table, which may be true or false both, right? Okay. Now we define. There is a question. Hmm. Now we define one definition that is called that rules of inference. So why do we need that? Because now we will see some methods of proofs. So whenever you want to prove a proposition, or if you want to prove something of compound proposition, then you see that you uses the truth table, right? But sometimes if the truth table has only two propositional variables, say P and Q, then you need 4 rows, right? Now, if you have 3 propositional variables, then you need 2 to the power 3, that is 8 rows. Now, what if you have more than 3, maybe you have 10 propositional variables. In that case, you need 2 to the power 10 rows, right? And this is a huge number, more than 1000. So therefore, by using the truth table, it is almost impossible to write the proof by hand, right? So therefore, what we will do? So in that case, we will not use the propositional argument. Sorry, we will not use the truth table. Then we will give some propositional arguments. Okay, and one of them is that rules of inference. So I define that. Rules for inference. Okay. Yeah. Any question? Okay. So the rules for inference is a tautology which generally used as building blocks to construct more complicated valid arguments. So that's mean, as I told you that for an example, so if an argument involves say 10 variables, or you can say that 10 propositional variables, then the truth table needs 2 to the power 10. This is a number of 1024 rows, right? So obviously this is almost impossible to do by hand. So thus it will be better if we use that rules for inference to complete the argument. Okay. Now we shall see some tautology which is very useful for the rules of inference. You have already seen some of the tautology. So first one is the tautology that P and P implies Q. This one implies Q. Now this is a tautology, right? Why this is always true? Because if P is true and P implies Q is true, so that's mean Q must be true, right? So therefore the hypothesis true implies the conclusion Q must be true. So therefore this is a tautology, right? And if that hypothesis is false, then this conditional statement is always true, right? So that therefore it is a tautology, and this tautology is generally expressed by the notation say P and P implies Q and this implies Q. Okay, that's mean if P is true and P implies Q is true, then Q must be true. Okay. Also, this is a tautology you can verify by the truth table. That's it. That's mean by using the true or false argument, and you need only 4 rows because you have only true propositional variables. Okay. Now similarly, we will list few tautology and some rules of inference. So here we list the tautology and here we list the
Sir,
yeah.
sir, in the above example, what is the rule of inference?
Which one? Here?
In this example, what is the rule of inference? Like,
Okay. So this one, this expression we call the rules of inference. So this is just a notation. and this one we called it tautology, right? Because this is a tautology.
Oh, okay, sir.
Okay, this is just a notation.
Yeah.
As I told you that in this logic chapter, there are something you have to remember, and there are some term you may forget that one because there are lots of terminology. So here, this terminology, that tautology, you have to remember that,
Yes.
right? But here the terminology that rules for inference, you can forget that
Okay, sir.
because that will not be much useful when you solve a problem. But the tautology, that term will be always useful. Okay, so here we are giving this argument that in this way we can prove a theorem. So for an example, suppose you want to prove a statement Q is true. Then what you can prove that? So you can prove that P is true and P implies Q is true. Then that will automatically imply that Q is true. So that is the argument actually. So by this rules of for inference, there will be these are the just building block of the arguments. So what is an argument? Argument is a sequence of propositions, right? And this is a proposition, that is compound propositions. Now if you can show that all of these premises are true, then ultimately you will get your conclusion is true.
Okay, sir.
Sir, what if premises contradict each other?
Premises contradicting each other. So see, that is a different issue. So what we are saying here, so if all the premises are true, okay, then that conclusion will be true. So if your premises are contradicting each other, then we cannot say anything. And there will be a something, so we will define now that proof by contradiction. That in that case, you will see that if there is something both are contradicting each other, then the main statement will be false. So we will see that proof by contradiction. When we come to that part, that proof by contradiction, you will see that. But here we are saying that if all the premises are true, then your that conclusion is true. Okay, but that's mean, so we are not proving that conclusion is true, so we have to prove that conclusion is true, then only we will see that we will say that that argument is valid. So if the premises are true but conclusions is not true, then the argument is not valid. Okay,
Will,
so
sir, will it also work vice versa, like conclusion is true, then or like in this case, if we take P as a false and Q as a true, then one of the premise is not correct, but the final answer will be correct.
right, good. So that will be, in that case, that will be trivial proof. So we will come all of this, we will come to that. So if your conclusion is true but hypothesis is false, then that is the statement is true, that conditional statement is true, and we will say it is a trivial statement. So we will come to that part. So here we are just saying that, so what we are trying to show here, so we need a valid statement. So okay, so we need a valid argument. So for that, we have a sequence of propositions where all the premises are true, and that will imply the conclusion is true. Then only we will say that this is a valid argument. That's all. And all the other parts, when that will be true, that one part will be false, the other part will be true. So these are all the different issues. We will come to that step by step. We will define everything, but here we are only focusing with that all the premises are true, and that will imply the conclusion is true. Then only we will say that the argument is valid. That's all. Okay, so we have some more tautology. For an example, if we take negation of Q and P implies Q, okay, then that will imply negation of P. So that's mean if Q is false and P implies Q is true, So that's mean P must be false, right? We know that. Therefore, minus P is true. So this is a tautology. Also, you can verify this by the truth table. Okay. And this tautology we can write in terms of rules for inference. This is in this way. That is minus Q, P implies Q, and therefore minus P. So here we are just listing all the rules for inference which you can use to prove a argument is valid or not. So that's all. So we are just listing few tautology. Now another important tautology is P implies Q and Q implies R. Okay, and then that will imply P implies R. So that's when if P implies Q and Q implies R, then P implies R. Now again you can verify that this is a tautology. And in terms of rules for inference, we can write it is as P implies Q, Q implies R. So therefore P implies R. Now another important tautology is that if P or Q, okay, say P or Q is true, that's mean either P is true or Q is true. Maybe both can be also true. And minus P. So first of all, P either P is true or Q is true, and here P is not true. So therefore Q must be true. So therefore this is also a tautology, and we express this as this. Okay, and there are some trivial tautology. One is P implies P or Q. So therefore it is just P implies P or Q. And another one is P and Q implies P. That is P and Q implies P. Okay. And another one is important, which you can also verify by the truth table. That is P or Q and minus P or minus P or not and. So negation of P or R. Now that will imply Q or R. Okay, again you can verify that. So minus P or R, therefore Q or R. So these are some important tautology, right, which you can use to prove an argument is valid. Okay. Fine. Now we also have some rules for inference for quantitative statement, and that is also very important, and you also know that. So rules, so rules of inference for quantified statement. So that's mean first of all. So what do you mean by for all x px? So that's mean for all x px is true. So therefore if you choose a particular x or particular c, then pc will be true, right? So that this will imply pc. That's mean pc is true. Okay, so this is one. And also some kind of converge is also true. For an example, suppose you want to prove that for all x px is true, then how to prove that? Suppose your x, the domain of x is a real number, okay, and you want to show that a function f say is continuous on a whole R, then how will you prove that? Do you check for every x? That is not possible, right? Then what we will do? We will choose an arbitrary x and we will see that for that arbitrary x the function is continuous or not, right? That's mean the argument p is true or not. And if this is true and if x is arbitrary, then we say that for all x px is true, right? So therefore pc for an arbitrary c, if pc is true for an arbitrary c, then we say that for all x px. Did you get this statement? So for an example, suppose it is given that a function say R2R, this one, and you want to check that f is continuous on R. Then how to prove that? So here you're actually the number of proposition is actually uncountable, because for each x in R you have to check that this is true or not, right? So your statement will be something kind of this px, this is f is continuous at x where x belongs to R. So therefore it is not possible to verify p for every x, right? Then what you will do? You will choose an arbitrary x and then you will prove that f is continuous at that point. And then you can say that for all x px, that's mean f is continuous at every point. So therefore f is continuous on R. So in this way we generally prove that for all px kind of argument. So you have already seen this, right, during your calculus course. Okay. Now another one is, so there exists x px. So that's mean there exists x such that px is true. So therefore that's mean pc is true for some element c. And similarly, if you want to prove that there exists x px is true, if you want to show that, then you just need to prove that pc is true for some element c, and that will imply there exists x px is true. Okay, so these are all the maybe you can say that important rules of inference. So these are the just building block to construct a valid argument. Okay, is that fine to everyone? Any question? Yes, any question? No? Okay. Anyway, we will come to this portion again. So maybe you are little bit doubtful that or maybe confused that how we will use these facts, right? So anyway, we will use this tautology. You have already used last time in the last lecture. I asked you, right, to prove a statement without the truth table, and you proved that. So that's mean you use some arguments, right? And each step of that argument, you use some compound propositions. So that is just a rules for inference. Okay, fine. Now we come to the portion Just few students asked that if this is false and that is true, that's mean conclusion is true, or hypothesis is false, or some premises are false, or some premises are contradicting. Then what will be the issue, right? You asked just. Now we will give the answer of that questions. Now this is a part of method of proving theorems. Okay, so how to give a proof of a statement. So there are many kind of proof. So first of all, one kind of proof is just called vacuous proof. You have already used this term, right? You have already used this term when you prove some theorem or some lemmas, right? And something, sometimes you write that, okay, this proves it is true, it is vacuously true. You sometimes use that kind of term, right? Now, what is a vacuous proof? So, if P is false, okay, then the conditional statement P implies Q is always true. Do you remember that fact? If your P is false, then this conditional statement is always true. Okay, in fact, it does not depend on P, depend on Q. P is false, then P am I audible? I just got disconnected.
Yes, sir, you're audible.
Yes, sir, audible.
Okay. Yes. So if P is false, then whatever the Q is, Q might be false or Q might be true. This conditional statement P implies Q is always true. Okay. Thus, we have a proof. Thus, we have a proof for the conditional statement P implies Q. Okay. Now this proof is called vacuous proof. You actually need this one. So you might uh, think you might be thinking that, okay, this is not very useful, but in fact this is useful. Why? Suppose you have a statement, this one example. Say your statement is if n bigger than 1, then n square is bigger than n. So suppose this is your statement. Okay. Okay. So if n is bigger than 1, then n square bigger than 1. And suppose your domain is say 0, 1, 2. So this is your domain. Okay. And this is your statement, say Pn. Okay. Now what can you say? Can you say that this statement is true for all n? So can you say that for all n Pn? That is true. Yes, we can say that because when n is actually bigger, suppose from n, if n is 2, n is 3, then we have a proof. But what if n is 0 or n is 1? Then this is also true by the vacuous proof. Then you have to write that for n equal to 0 and n equal to 1, this the proof is the proof follows from the vacuous proof, or you can say that this is vacuously true, and then you can start from 2. Okay. Now here P0, so this one is the statement if 0 bigger than 1, then 0 square bigger than 0. So you can take this is your P, you can take this is your Q, and since P is false, no, right. Now since P is false, so therefore P implies Q is true. So this is a vacuous proof. So therefore P0 is true using vacuous proof. Oops. Any question? Okay. No, I don't know. So there is some noises. So if you are not asking, then please mute. Okay. And obviously, if you want to ask something, you then please unmute and ask.
Sir,
Mm-hmm.
am I audible?
Yes, yes, yes.
Sir, if P is negative, then we can also prove this by the backwards proof.
No, say again. It is.
Sir, if the domain is negative, if negative numbers, let's say -2, -3, this type of numbers, then we can also prove this by backwards proof that this is true.
Right, right, yeah.
Okay, sir.
Yes, because that whenever your hypothesis is false, then you can always say that.
Yes, sir.
In fact, your domain you can take Z as well. Right. You can take your
Yes.
domain Z as well. That is fine. Okay. So I'm giving here just an example. Now the another part is trivial proof. Again, he used that term whenever you are writing some proof of a theorem of lemma, you generally write that okay, this is trivially true, right? This portion for n equal to 1 or something, it is trivially true, and then you start from the other cases, right? Now, what is actually a trivial proof? Now, sometimes people mix that vacuous proof and trivial proof. So even we also mix sometime, but that should not be the case. We have to be precise about what is the vacuous proof and what is the trivial proof. They are different, not same. But sometimes we mix that. So what is a trivial proof? Now if Q is true, then the conditional statement P implies Q is true. Again, here, or you can say that these does not depend on P, right? Now, since your Q is already true, so therefore whatever the hypothesis P is, P might be false, P might be true, but that does not matter. P implies Q is always true because your Q is true. Okay, so therefore we have a proof for the conditional statement P implies Q, and this proof is called trivial proof. Okay, so we can write that this. So thus we have a proof for the conditional statement P implies Q. Okay, now this proof is called a trivial proof. Now here is one example. So for an example, your Pn is the statement that if A and B are two positive integers, with A say greater equal to B, then A to the power n bigger equal to B to the power n. Okay, now this is your statement. Now what about P0? So can you say that P0 is true? Now again, for this you don't have to prove this because this is true trivially. Because if you take n equal to 0, so first of all, let P equal to this one, that A and B are two positive integer with A bigger equal to B. So this is your P proposition, and Q proposition is A to the power 0 greater equal to B to the power 0, because we are trying to prove P0. Okay, now see that this is 1 and this is 1. So therefore Q is true, right? So this is the meaning of this one is greater than or equal to. So here we have the equality. So therefore it is true. Therefore Q is true, right? Now since Q is true, so therefore the conditional statement P implies Q is also true. That's P implies Q is true, right? So therefore we have a proof for P implies Q. Now this proof of P implies Q is called a trivial proof. Okay. So that's mean if you are going to prove a conditional statement, that's mean if something then something. Okay, then if the hypothesis is false, then the proof is correct, and that is the proof by vacuous proof. And if the conclusion is true, then also the proof is correct, and that is the proof by trivial proof. Okay, so these two are very simple. So any questions up to this? Now we have some other types of proof. So we have some have direct proof. So sometimes actually the direct proof will not work. And in that case, we need some other kind of proofs. So proof by contradiction, proof by contrapositive arguments. So these are the types of proofs. Okay. So first of all, we see what is a direct proof. So that does not mean that every proof will always work. Okay, it might happen that direct proof does not work sometimes. In that case, you can go for the other types of proofs. So what is a direct proof? So a direct proof shows that a conditional statement P implies Q is true by showing if P is true, then Q must be true, or you can say it is directly. Okay, so directly we will prove that if P is true, then Q must be true. So if we can prove directly this, then this proof will be called a direct proof. Okay. Now see one example. So using direct proof, show that if n is odd, then okay, there is a problem with my pen. Okay, let's show it. Oops. Ah, now it is working. Okay. Now if n is odd, then n square is odd. Okay. And here domain. Again, there is a problem. So domain is the integer. Okay. My pen again does not work. Okay. So remember that here this proof is very simple. We know that proof is very simple. So don't focus on the proof. So here we will give three types of proofs. One is direct proof, one is proof by contradiction, one is proof by contrapositive arguments. Okay. But don't focus on the proofs because that proofs will be very simple. Okay. Just focus on the logic. So how to use these logical statements to prove this different kind of proofs. Okay. So how to prove this? By using direct proof. So let P be the statement n is an odd integer. Okay. And Q be the statement n square is an odd integer. Okay. Now we need to prove that P implies Q. Okay, so we need to prove that if P is true, then Q must be true. See, the proof is simple. So if P is true, then P is an odd integer. So therefore P can be written as some 2k plus 1, right? For some integer k, right? Oh, not P. N equal to 2k plus 1, right? Now then n square equal to 2k plus 1 whole square, that is 4k square plus 4k plus 1. So that is 2 into 2k square plus 2k plus 1. So we can write it is as 2k dash plus 1, where k dash equal to 2k square plus 2k. This. Now since n square is of the form 2k dash plus 1, so therefore n square is odd, right? So therefore Q is true. So we prove that if P is true, then Q must be true. So thus P implies Q is true. Okay, and this proof is called a direct proof. Okay, so this direct proof sometimes may not work. For an example, suppose we need to prove that the similar statement should prove that if n is an integer, then sorry, n is always integer. If 3n plus 2 is odd, then n is odd. And here domain is Z. Okay. Now, if you want to prove this by the direct proof, then you will see that this does not work. For an example, let P equal to 3n plus 2 is odd, not equal to, so this is the statement. Okay. And Q is the statement that n is odd. Okay. Now, if P is true, then 3n plus 2 equal to some 2k plus 1. Now that implies 3n equal to 2k minus 1. This. But from this, you cannot conclude directly that n is odd. So, cannot conclude directly that n is odd.
So,
Okay, right, yeah.
so if we write 3n plus 2 as 2n plus n plus 2, then we have 2 common and n plus 1 plus 1. So it's just 2k plus 1. So it will be odd, right?
I did not get what you are saying.
We should rewrite 3n plus 2 as 2n plus n plus 2.
2n plus n plus 2, okay.
Okay, sorry sir, then okay, I took the precondition that n also should be odd. Okay.
Right. So
Sir,
yeah,
like,
you can
what do we do in terms of modulo?
no. See, you can always prove that. So what I am saying that you cannot conclude directly that n is odd.
No, sir. Like, if we take in terms of like modulo 2.
Modulo 2, okay.
So then 3n plus 2 again you can write as 2n plus n plus 2. 2n modulo 2 is 0, and 2 modulo 2 is also 0. So 3n plus 2 modulo 2 will be equal to n modulo 2.
Right.
And if 3n plus 2 is odd, That means that 3n plus 2 modulo 2 is 1. That means n modulo 2 is 1. That means n is odd.
Right. Yeah, in that way, I think we can say.
Sir, why we cannot say that n is odd from here since RHS will be odd now?
What you are saying?
Why cannot we conclude from here that n is odd?
No, that is not clear. Actually, your voice is not clear.
Why cannot we conclude from here that n is odd since 2k minus 1 will be odd and 3 multiplied by any odd number will give odd and multiplied with even number will give even.
Yeah, that's what I'm saying, that you cannot conclude that directly by the fact that anyway you can always prove that because that is true, but you cannot prove directly in the sense that you need some more arguments to conclude that, or you are using some fact. For an example, he uses that modulo argument, right? So
Sir,
uh,
there is another way that earlier someone said that we can break 3n as a 2n plus n.
hmm.
And in the last line, we will write 2n plus n is equal to 2k minus 1.
Okay.
Then we can write as n is equal to 2k minus 1 minus 2n,
Then it is
which can be written as
right,
2 times of k dash minus 1.
right. -1, right? Yeah. Right. That is also fine. Okay. Shall we be using some other fact? Okay, anyway. So that is fine. But anyway, so it looks like that in that way, in this way also you can prove that n is odd. But sometimes there are some proofs, not this one, but there are some proofs that if you go with the direct proof, it might be some lengthy, the proof might be lengthy, and sometimes you may not conclude that, right? But if you go with the reverse way, that is that contrapositive argument we will define, then that proof will be very easier. That's mean if you want to go with direct proof, the proof will be lengthy and some additional complicated statements, not this one, but in general. But if you use that contrapositive arguments, then that will be very simpler. For an example, here also you are giving some arguments here, giving some extra arguments. But if you use that contrapositive arguments, then that part will be very simple. So you don't have to use mod, or you don't have to use or you don't have to manipulate anything. But anyway, these proofs are also correct. So I was wrong that you cannot conclude directly, but you can conclude. But you need to do some manipulation only, right? Okay. So your voice is very slow. So anyway, that is fine. So we are now defining proof by contradiction. Sorry, not proof by contradiction. We first define proof by contraposition. That's mean proof by contrapositive arguments. Okay, so what is the contrapositive arguments? So we know that P implies Q, that is equivalent to minus Q minus P. Okay, so this. So we know this one. So therefore, so to prove P implies Q is true, it is sufficient to prove that Sorry, there is some problem with my pen. Okay, now it is working. Sufficient to prove that minus q implies minus p is true. Okay, now this proof is known as proof by contraposition. For an example, again, if we come to this one, so some students do this by using modulo term and doing this manipulation, right? But if we use, also you can use some different example as well. If we use that contrapositive arguments here, then that will be very trivial. For an example, here P is this, Q is this. So if we look at the previous example, then what is my minus Q? Now minus Q is N is not odd. So that's mean N is even. And what is minus P? Minus P is again 3N plus 2 is not odd. So this is even. Right? Now it is easy to prove that minus Q implies minus P. Why? Since minus Q is odd, sorry, minus Q is even. That not minus Q is even, that is. Now assume minus Q is true. Now then N is even. So N can be written as 2K, right? So therefore 3N plus 2 that can be written as 3 into 2K plus 2. So that will be 2 into 3K plus 1. So this is some 2K dash. Okay. So therefore 3N plus 2 is also even. And that imply minus P is true. So therefore minus Q implies minus P is true, and which is equivalently P implies Q is true. Right? Now this is kind of proof is called a proof by contraposition. Now this is a small exercise. Now can you prove that if m square is even, then m is even? Okay. Now what you do? First prove it is directly and see how the proof goes, and then use the contraposition proof by contraposition. That's meant proof by the contrapositive arguments. Now if you use that contrapositive argument, then proof is very trivial. Okay. So by contraposition, proof is very trivial or very easy. Okay. Now you try to prove directly. Okay. So you just use proof by contraposition and then try to prove directly, and then you can compare both of them. Okay. So I did not try to prove it directly. So you can try. Okay. So there is some another proof, that is a proof by contradiction. Now, what is a proof by contradiction? Now, suppose we want to prove that a statement P is true. Okay. Now remember that here we are not focusing on the conditional statement. Okay. So here we are focusing only a statement P. Okay. Now suppose we want to prove a statement P. Then what do you mean by we will prove P by a contradiction? So that's mean we can find a contradiction Q okay, or you can say that minus Q implies P is minus P implies Q is true. Okay. Now since Q is a contradiction, Q is false, right? So therefore minus P, that is negation of P, must be false. So therefore P is true. Now since Q is false, so negation of P must be false. So that is P is true. Okay. And this type of proof is called proof by contradiction. Should write here proof by contradiction. So this type of proof is called a proof by contradiction. Okay. Now the question is how to find a contradiction. So how you can find a contradiction? So that's mean to find a contradiction, so we need to find a proposition R. Remember that we need a proposition, okay, R, such that minus P or negation of P implies R and negation of R. Now this is called a contradiction. So R and is therefore minus negation of P implies a contradiction. Now we will see one example. Now prove that root 2 is irrational. Okay. Now how to prove it by contradiction? So let P be the statement, this one, root 2 is irrational. So that's mean what is minus P? Minus P means root 2 is rational. Okay. Now since minus P is true, now assume minus p is true. So that's mean root 2 is rational. So therefore root 2 can be written as m by n, where n not equal to 0 and m and n are relatively prime. Okay. Now if we take that, if you do the square on the both side, you will get that m square equal to 2n square. Okay. So therefore m square is even, and that imply m is even. It is by our exercise. Okay. Now since m is even, therefore m can be written as some two k.
Sir, your
Imply
voice
n
is
is
breaking.
sorry, your voice was not clear.
Sir, your voice was breaking in between.
Oh, my voice was breaking. Okay, okay. I don't know. There is some internet issue. I don't know why it is. Because I did still. And also I switched my video for that one. I switched off my video, but still. Okay, anyway, that part is clear. That is very simple. So I will make sure that there should not be any voice breaking. So n square, we got m is even and also n is even. Okay. So now can is R, what is contradiction and what is R here? So you can say that this is a proof contradiction, but that will not work here. You have to be precise here in this logic, because here is proof. Here main focus is not the proof. Main focus is, do you know the proof or not?
Sir, we can take R as the statement M and N are relatively prime.
Right.
And then not R would be that they have a common factor.
Right.
Good. Both are true. So
right.
R and that. Yes.
So we need to take here R is the statement that M and N are relatively prime. Okay. So therefore negation of P implies R here. They are relatively prime. And also this implies minus R or negation of R because they have a common factor. So this means 2 is a common factor of M and N. And minus R means M and N have a common factor. Right? So thus negation of P implies R and minus R. This is a contradiction. Is true or is false. That implies P is true.
Sir, please explain this line once again, how this is a contradiction.
Okay. So what we got, we have assumed that P is false. Sorry, minus P is true. Okay, so what is minus p or negation of p? That's mean root 2 is rational. Now what do you mean by root 2 is rational? So this is my statement. So negation of p is the statement that root 2 is irrational. So therefore root 2 can be written as m by n where n is not equal to 0 and m and n are relatively prime. You know that. That is the definition, right? Now if root 2 is rational, then root 2 should be expressed as m by n where n not equal to 0 and m and n are relatively prime. Now if we take the statement R as m and n are relatively prime, then negation of p implies R, right? Negation of p implies R. And similarly, if we do this manipulation, then we get that m is even, n is even. So therefore 2 is a common factor of m and n. Right? So therefore m and n has a common factor. So therefore negation of p again implies minus r. So therefore negation of p implies both r and minus r, and that is a contradiction. That's when r and minus r, this is a contradiction. So this is a contradiction. So that's mean negation of p implies a contradiction. Okay, is that clear? Yes.
Yes, sir.
Okay. So what is this blur? That skin was blur. So I don't know, because of that I also switch off my video, but still I don't know why there was some network issue. So I will try to fix it from the next lecture. So I will see the recording and I will figure out that how this was working.